Today we're going to talk about conditional probability, intersection, and independence. Events A and B are independent if the occurrence of A does not affect the probability of B occurring. Spin the spinner twice, find the probability of landing on yellow and then purple. We can see there are 6 pieces of the spinner. We have one that's yellow, we have one that's purple. So the probability of landing on yellow would be 1 out of 6. When we spin the spinner again, we have a probability of 1 out of 6 of landing on purple. We can multiply 1 times 1 is 1, 6 times 6 is 36. And the question we should have is, did getting yellow on the first spin change the probability of purple on the second? And the answer is no. It didn't matter what we got on the first spin. The 2 events are independent. The probability of getting purple had nothing to do with getting yellow. So that's what we mean by independent, that there's no effect of the 2 events. Let's try it again. We're going to spin the spinner twice, and we're going to find the probability of landing on an even and then a green. Even means I'm going to land on either a 2, a 4, or a 6, so there are 3 out of the 6 choices. And then landing on green, there's only one green. It's the 3, so that's 1 over 6. We can multiply across. 3 times 1 is 3, 6 times 6 is 36, and then remember, just reduce the fraction. That'll become 1 over 12. Let's look at cards. We're going to pick 2 cards from a standard 52 card deck without replacement. So what that means is once you pull a card, you're not going to put it back into the deck. You're going to hold on to the card. When we look at each kind of card, we have 4 kings, 4 queens. So let's start with that, saying we have 4 of each type. So first time I pick a card, the probability of getting a king would be 4 out of 52. So of the 52 cards, 4 were kings. Then the next time we go, we're going to pick a queen. So we haven't picked a queen yet, so there are still 4 queens left, but we don't have 52 cards anymore. We have 51. So picking a card, picking the king first, changed the probability of getting a queen. It changed it because the denominator changed, right? So these are dependent. I can see that difference in the denominator. It doesn't make a big difference for us, but it's just something to point out that there is this little bit of difference we have to think about. If I'm holding a card in my hand, I have less cards to pick from. Again, we can put this in our calculator. I would probably want to maybe reduce it first. Say 4 over 52 is 1 over 13, and then times 4 over 51. 4 times 1 is 4, and then let's just multiply 13 times 51 gives us 663. Okay, so there's our first probability here. The next one says club then diamond. So we have 4 suits. There's 13 of each suit. So when I look at the probability of getting a club, well, there were 13 clubs out of the 52 cards. And then the next time I pick a card, I haven't picked a diamond yet, so there's 13 diamonds left, but again, we have 51 cards left. So there's just that same little bit between the 2 that there's dependent because I held on to the card. 13 over 52 reduces to 1 over 4. 13 over 51 does not reduce, so I can multiply 1 times 13 is 13, and let's do 4 times 51, and this gives 204. And the last one says both hearts. Okay, so hearts. We're thinking just like the clubs and the diamonds, I have 13 hearts out of the 52. Little bit different this time because now that I hold a heart in my hand, it means there's only 12 left in the deck. So we do see that little difference this time of the numerator changing as well. The denominator is 51 one more time. This one I think would be a good one to go over and see, like, how could I put this into maybe like Desmos? Because I do like you to see the different ways that we can do simplifying for fractions. Right. So here we are in Desmos, and I'm going to put those 2 fractions in. So remember, we started with 13 over 52. And then I'm going to multiply by 12 over 51. See, it immediately gave me a decimal, but there's this nice little button here. It says convert to a fraction. It says our answer is 1 over 17. So let's go back and put that into our slide. So now we know this is 1 over 17. Same questions again, but this time I said let's do this with replacement. So when I take out a card, I'm just going to put it back in. Well, we know there were 4 kings out of the 52 cards. What's happening this time is when I go to pick a queen, because I put the card back in, I have 4 over 52 again. I've forced these to be independent by putting the card back in the deck. 4 over 52 is 1 over 13. I have that twice, so I end up with 1 over 169. Okay. Club, then diamond. Well, we said there were 13 clubs out of 52 cards. And because I put that card back in, I have 13 diamonds out of 52 cards. 13 over 52 is 1 over 4. Again, I have that twice, so I end up with 1 over 16. Both hearts, 13 over 52, because there are 13 hearts in a deck, and I put that card back in, so I still have 13 over 52. So this time I have the same answer as I did for the previous one, which is 1 over 16. So what do we find here? That these are independent events if I replace the card in the deck, versus these are dependent events if I hold on to the card. So we're just looking for, does that make a difference, or is it the same? Right? So we're looking for independent versus dependent. Okay. So let's take this farther and let's roll a die. So we're going to roll a die twice. So I'm not going to have 2 dice like my picture. I just have 1 die and I'm going to roll it twice. So let's look at the probability of getting a 1 and then getting a 2. So getting a 1, there's 1 out of 6. And then I roll it again. So I have a 1 out of 6 chance of getting a 2. This is 1 over 36. How about getting a 4 and then getting another 4? Same thing. 1/6 chance of getting a 4 each time that I roll. So I have 1 over 6 times 1 over 6, which is 1 over 36. Sometimes you'll see homework that might say get a 1 and a 2, like it's the idea that you roll it twice and then you get a 1 and then get a 2. That's okay. It's just wording, so pay attention to the wording and see that things could be equivalent, just said a different way, just because that's how we speak. Nothing, no one's trying to trick you. It's just different people have different ways of expressing the same information. All right, so here let's see the probability of rolling a 5 4 times. So I kind of think of this as like the counting principle, that I have 4 tasks to complete. I have to roll it 1, 2, 3, 4 times. Every time I roll, I have 1/6 chance of getting a 5. So I'm going to put this 1 over 6 in here 4 times. The 1 times 1 times 1 times 1, that's just 1, and then 6 to the 4th is 1,296. Okay. Then the last one on this page says, what's the probability of rolling an even, and then a number greater than 4? So pay attention to this. Sometimes it helps to just write it down. So even we know is 2, 4, and 6, so we have a 3 out of 6 chance of getting an even. Greater than 4 does not include 4, so I'm only talking about 5 and 6, so that's 2 out of 6. You can multiply the top. 3 times 2 is 6 over 36. This reduces to 1 over 6. Next, we want to look at something called conditional probability. The probability of event A occurring can often be affected by knowing another event has occurred. Let's take an example. Say I'm thinking of a former president. Can you guess who I'm thinking about? Right? There's lots of choices, so it's really hard to tell what am I thinking. But let me give you this other clue. What if I say I'm talking about a former president and I'll tell you ahead of time that he was the first president? Do you know who I'm talking about now? Hopefully you said George Washington. Me giving you that extra information is conditional, right? I gave you a condition. I said he happens to be the first president, and then it gives you kind of a clue. That's what I'm thinking about with conditional probability. I'm giving you more information, and that changes the probability of what we're doing. Here's the formal definition, really, is the probability of A given B, and that's how I write this, or read this. This is the probability of an event A occurring given B already happened, so I'm telling you something ahead of time. So we can look at it 2 ways, and we'll do both of these calculations. We can do it as the probability of A and B over the probability of B. We can also do it as the number of A and B over the number in B. Big deal is this B, this is our condition, becomes the denominator. So it's either the probability if I give you that kind of information, or it's how many times B occurred if I give you that information. So let's look at that a little farther. Right. Here is information on colorblind. So I found this in an article, and I thought this is a good way to talk about it. So this is exactly how it was in the article. So they said the number of people that they looked at was 1,249. 612 of those people were men, 637 were females, and then it broke it down to if they were colorblind or if they couldn't determine if they were or not. So we had 32 males that were colorblind, 1 female, for a total of 33 people. And then the ones they couldn't determine, we had 2, 4, and 6. I'm going to stick to the colorblind part. So in general, let's first say, what's the probability somebody was colorblind? Well, this would be 33, the total people that were colorblind, over our total set, 1,249. I think for perspective, I'm going to go ahead and make these percents. So this says 2.64%. So the second one says, well, what's the probability they were colorblind given that they were male? So I'm only looking at the men this time. So there were 32 men that were colorblind out of the 612 men in the survey. So really important that you see the denominator switches when I give this conditional. So I have 32 divided by 612. This says 5.23%. Let's do the same thing. Let's switch it to women. So I look at, there were a total of 636 women in this survey, and one of them was colorblind. 1 divided by 637, this comes out really small. This is 0.00156. We're going to call this 0.16%. So big difference in looking at the numbers a different way. I'm going to flip these around, so it's going to feel like I'm doing the same thing again, but I'm not. The first one we already know, this was just for comparison. This is 2.64%. Now I'm going to say, what is the probability that a person is male given they're colorblind? So if I tell you ahead of time that, hey, this person that we're talking about is colorblind, there's 33 of them. The probability that it's a man, well, there are 32 out of 33 men that are colorblind. So 32 divided by 33, we're going to call this 97%. So if I know the person's colorblind, very, very high likelihood that that person is a male. Let's look at the women. A female colorblind, well, there are 33 people that were colorblind. So see how this C becomes the denominator, and there was 1 woman. Well, 1 over 33 is 3%. Let's say again, because I know it can be confusing, what's the difference between these two slides that we did? On the last slide, I had probability of colorblind given male, and that came out to about 5.4%. This kind of says, like, of males, about 5% of males are colorblind. Versus male given colorblind says 97% of the people that are colorblind are male. So this is a study I read, I think it's from the UK, and it talked about, is there a connection between blood type and the severity of COVID? So what they looked at in this particular study is of the people that were brought to the hospital, how many were just hospitalized or how many ended up being on a ventilator. So I called ventilator V, we'll call hospitalized H, and then the blood type that they broke down was either a person had A or AB blood type, or they had blood type O. 95 people that this report is on. So it says, what's the probability somebody was on a ventilator? So we can see there are 67 people on a ventilator out of the 95 people in total. 65 divided by 95 comes out to 70.5%. And they said, well, what's the probability someone is on a ventilator given they have type O blood? What happens? 57, that's type O, that becomes our denominator. And then we look at how many people with type O were on a ventilator, that was 35. 35 divided by 57 gives us 61.4%. Well, what about somebody being on a ventilator given that they have A or AB blood? So A or AB blood, that's 38, there's our denominator. And then we can see there were 32 people that were on a ventilator. So 32 divided by 38 says this was 84.2%. We can see there's a big difference in the outcomes, right? People that had A or AB blood were more likely to be on a ventilator than people with type O blood. Just to switch up our percentages and do percents instead of just raw numbers, we have these race participants. So I said, let's look at the probability somebody was 18 to 25. This says 0.60. How about somebody was in the 5K race? This was 0.55. So I'm just reading right now. So because it doesn't have any conditional yet, I'm just reading the numbers. Then let's do 18 to 25, 0.60, times 5K, which is 0.55. Okay, so sometimes you're just answering the questions and it doesn't matter if it's kind of weird what they're asking. So look at, I did 0.60 times 0.55 and I got 0.33. Okay. Let's look in the chart and say, well, what is 18 to 25 and 5K? So 18 to 25 here, 5K here, it happens to be 0.33. See how these are the same? This tells us something about this particular data, and it says this data shows that in this particular situation, being from 18 to 25 or being in the 5K, we're independent. And here's what that means. A and B are independent events if the probability of A times the probability of B is the probability of A times B. And that's what I just showed you, that when I multiplied the probability of 18 to 25 times the probability of 5K, I got the same thing as doing the intersection. This was really forced in this example. I made this happen because I made up these numbers. But in life, if we could go back to something like the COVID and the ventilators and see if I found the same thing between, let's say, the probability of B times the probability of O, if that was the probability of V intersect O, then I would say, oh, there's no relationship between being on a ventilator and having type O blood. We can clearly see here, if we do 67 over 95, that was our ventilator, and then type O blood was 57 over 95. And if we just kind of say, is that equal to the probability of V intersect O, which is 35 over 95? Let's check that out. So I'm going to do 67 divided by 95 times 57 divided by 95. This gives me about 0.423%. And then 35 divided by 95 gives me 0.368. So this says these are not independent events, that there is some link between blood types. That's kind of how we use this conditional and the independence in the real world to say, are things linked? Can we see something that tells us somebody's more likely to do something based on some other information we have? So that's why we like to look at this independence. All right. It can also tell us that things are independent if we do the probability of A given B and we still get the probability of A, or we do the probability of B given A and we still get the probability of B. Where have we seen that? Like when we did the spinner, right? We said like, oh, getting yellow and then getting purple. It didn't matter that I got yellow the first time. The probability of getting purple was still 1/6, right? Even though I knew I got yellow the first time, it didn't change anything. So with independence, I can see that knowing something doesn't really help me. All right, let's look at something else. So this is from a website where they look at Chicago shootings, and this is pretty current. Today is November 14th when I'm making this video, and this was November 8th. So this is in the past week, how many shootings there were. I just transferred that into a chart that we could look at a little better. And let's find the probability. So this is from someone that was shot, that they were killed. We can see the total number of people killed was 669. Of the total shootings was 3,465. So 669 divided by 3465. This says 0.193, so 19.3%. Okay, let's say what's the probability somebody was shot in the head? So when you look, there's 299 people were shot in the head out of the 3465. This says about 0.086%. All right. Now let's look at the probability that somebody was killed, so they died, given they were shot in the head. So the first thing that happens is this number, 299, goes on the bottom. So I'm only looking at people that were shot in the head, and it says 180. So 180 divided by 299 gives us 0.602. So it says if you get shot in the head, more than 50% chance you're going to die, right? So a higher probability of death if you get shot in the head compared to the 0.193% if you just get shot, right? So the 0.193 says 19.3% of people die, but if you got shot in the head, you have a 60% chance of dying. Let's just compare to something else. So let's say you got shot in the back. So there are 289 people that got shot in the back of the 3,465 people. So 289 divided by 3,465. That's 0.083. Okay. Now let's look at wounded if you're shot in the back. So back, 289 becomes the denominator. So whatever is given goes in the bottom. Now let's look at wounded shot in the back. So I can see there were 247. So 247 divided by 289. This is 0.855. Okay. So it says you get shot in the back, most likely you're just wounded, like you're not going to die, right? In total, what's the probability if you get shot that you're wounded? 2,796. Just put that in there. Over 3,465. So 2,796 divided by 3,465. This gives me 0.807. You should expect that anyway. Remember we said there's a 19.3% chance that you die, which means there's an 80.7% chance that you live. All right, so let's go back to cards just to make sure we've done a little bit more. We're going to pick 2 cards from a deck of 52, and we're going to say what's the probability that we get an ace on both. So I have the first card is an ace, second card is an ace. The cards are drawn without replacement the first time, which means we pull the card and you hold on to it. So the first time to get an ace, there were 4 aces out of the 52 cards. But then we held on to it, no replacement, which means there's only 3 cards left out of the 51 cards left. So 3 aces of the 51 remaining. 4 out of 52 we can reduce to 1 over 13. 3 over 51 actually reduces to 1 over 17. So let's just multiply 17 times 13 and we get 1 over 221. I'm going to change it just slightly and say next time let's replace it. So if we're going to replace it, there are 4 aces out of 52 cards at first, but then I put the card back in. So again, there are 4 out of 52. This time this is 1 over 13 times 1 over 13. This is 1 over 169. Okay, let's look at some conditionals with cards. So we're going to pick 1 card, not 2, from a deck of 52, and we're going to say what's the probability that it's black given it's a heart. Okay. Well, there are 13 hearts, but all hearts are red, so there's a 0% chance that we got a black card. And then I said club given jack. Well, there are 4 jacks in the deck, and one of them would be a club. Let's look kind of the same, right? I just flipped it around and I said, well, what's the probabilities of jack given it's a club? So there's 13 clubs and then one of them's a jack. So what you're seeing every time is whatever's given goes in the denominator. Given goes in the denominator. Lastly, let's say a class has 12 business majors, 8 nursing majors, and 8 liberal arts majors. 2 are selected at random. Let's find the probability that both are business majors. Okay, when we're picking 2 people, we can't replace it. I can't have the same person twice. So we're thinking we pick one, they stay, then we pick another one. So both are business majors. Let's start with 12, 8, and 8 is a total of 28 students. So to start, I had 28 students, 12 were business majors. Then the next time, there are 11 business majors left out of 27 students left. So I'm going to do 12 times 11, which is 132. And I have 28 times 27, which is 756. And then I'm going to have my calculator reduce that for me. This becomes 11 over 63. Okay. Neither are business majors. So 12 people are business majors, 8 and 8 is 16 are not. So I have 16 over 28, and then I have 15 over 27. Again, the idea that once I pick somebody, I have one left, I have one left. So 16 times 15 is 240, and then 28 times 27, this is 756. 240 divided by 756 gives me 20 over 63. And remember, you can always go back to Desmos, have Desmos do the multiplication for you. I want to see you use technology. The hard part is setting up. I don't want you like worrying about doing fractions.